Hey guys, so maybe we'll get started. I don't know if someone was supposed to introduce or whatever, but it's like 11:10, so probably want to like keep the schedule like, I don't know, somewhat, at least somewhat on track. So how's everyone doing? Like, good. So good morning, everyone. Welcome to Oakland. Is everyone having a good time here? Yeah? Yeah, as you can tell, I'm an Oakland A's fan, and I'm also a Raiders fan, so I'm a big, local person. I actually no longer, that's right. Yeah. I don't think we'll make any enemies, but, I don't know. If you're a Giants fan, feel free to leave or whatever. No, I'm just kidding. No, but it's really good to be here. And let's see if we make sure my display is up and running. Ah, there we go. All right, awesome. So yeah, we'll get started and talk a bit about really interesting stuff that I've been working on to bring. I think almost everyone here knows about. Actually, we'll just get a really quick show of hands. Like I think everyone knows about Spark. Who's I guess I would say like raise your hands if you're just learning about Spark. And raise your hand if you're using it in production. Okay, cool. It's hard to tell. Like sometimes I see like the same hands shoot up. And how about Cassandra? How many of you guys are using Cassandra? All right, awesome. So yeah, this talk will be great for you. I think that. Oh. Okay. Right. Anyway, so. Just a little bit about myself. I've been using Cassandra and Spark for a very long time. Cassandra since really early days, the 0.6. I don't know if any of you guys remember that. And Spark since 0.8. And I've been contributing to Spark for a while. There's one file at the root of the Spark repo that was contributed by me that you'll find, which is pretty cool. But I also maintain the Spark job server. And today we'll talk about OLAP on Spark and Cassandra and some things you can do to get really good OLAP performance, as well as some new and exciting open source projects. A little bit about my sponsor. I'm a part of TupleJump. Most of you have probably not heard of them. So what we are is we are a big data technology leader that specializes in Spark and Cassandra. We have a bunch of pretty interesting open source projects. One of them is a Spark and Cassandra connector. Another one is a Lucene indexer for Spark, and another one is an HDFS plugin for Spark. Basically, you can run that. So some interesting projects. Well. I don't know, there's some of you, I don't know if in case you've attended, I gave some similar talks at Cassandra Summit last year. This talk has a similar title, but it's actually, most of the content is actually very different. So here's a problem space. Let's say that I have a lot of data and I want to run fast analytical queries on OLAP queries on structured data. And what I mean by OLAP, just to clear up that term, because sometimes there's a lot of confusion, is that I'm interested in analytical, like say, mathematical queries. Like let's say I want to find out what are the top items in this kind of category, right? Or I want to run certain kind of statistical things, like what is the variance or a correlation between two things. And this problem space, and let's say that I'm really interested in flexibility. Like I don't want to be limited to just a few like pre-aggregated items. I really want to give people the power to run ad hoc or at least have very flexible kinds of queries on structured data. What's more, I have data that is constantly coming in, which is almost always true. That I really care about running queries over fresh data. So how do you solve this problem? All right. And an example is, give you an example from video analytics. let's say you have many billions of new events every day, and that every time, let's say someone watches some video on a consumer website, you get some new data when you are playing a video, when you fast forward, or typically what will happen is that every say minute or every n seconds as you're watching this, you get some feedback, so that you can know if someone skips ahead, or if there's some ad that people don't like, or something that you can figure out. And typically, publishers want analytics on the latest stuff. And the sooner you can get it to them, the better. Now, what some products people have built in this space is that you can have some dashboards. And dashboards are fine, but you can only get at really the top level kinds of information. Like I find out what are the top countries. But what people really want to do is to be able to drill down on specific answers, such as, let's say I want top countries, but it's filtered by a certain kind of device type, or OS, right? Or I want to drill in to a particular, let's say for Android devices, what are the top countries, as opposed to iOS, right? So the more insightful questions that you want to ask, then the more flexible kind of queries you want. And the problem is that as you drill down more and more, it gets the amount of pre-aggregation you would need to do to answer all these queries becomes too big of a combination, right? And so some requirements that we might have for a solution is that we want something like this to be, first of all, it has to scale to a lot of data. You're getting billions of events every day. So we can't simply throw an RDBMS at it. And we want to be able to easily ingest and update new data. So I'm not talking about traditional, say, OLAP cubes that are generated, say, once a day. I mean, that might work for certain kinds of queries, but let's say that we wanted something fresher than that, right? And want to support, flexible queries and, hopefully something open source. So why not use Parquet? Parquet is, universally used. It has excellent support in the industry. The only thing is that Parquet is really read optimized. It's a file format that when you want to write a lot of data, one problem that you might have, for example, is that you want your pipeline to be resilient. That means that if you have an error, you want to be able to retry. And typically that requires you to have an idempotent data store. Or the other pattern is that you might end up writing the same data twice and appending to a file. Then what you have to do later is that you end up having to run a deduplication job, which takes your original Parquet files and generates a new set that has the data deduplicated. And that works, but that causes, that's another step you have to manage, and that causes a delay in when the data is available for processing, right? It's also optimized for writing very large chunks, very large and narrow chunks. If you think about the shape of the data that's coming in, Parquet works very, the thing is, because it's based on HDFS, it has to generate very large blocks of data. The typical block size in HDFS is like 64 megs. So that means that I have to, in order to fill 64 megs, I actually need a lot more memory than that just to do the columnar conversion and do a whole bunch of stuff that's necessary. So it works really well when I have it, I'm writing a few files at a time, but let's say that I have a very wide write pattern with where I want to segregate data, let's say for IoT, then that pattern doesn't work as well. And what I would say is that what people would ideally like, but don't have right now, is that you would really like a database abstraction for writing data into something that you can also read out very fast. So something that is write optimized, but that can later be read optimized. It turns out this problem has been, as most of the problems and architectures that we talk about today, most of them have been solved before, and this problem has been solved for many decades actually, with MPP databases, so-called, like Vertica. And there was a new article that even Facebook now has the world's largest installation, which is pretty interesting. That considering that Facebook created Cassandra and a lot of other technologies, right? And the typical architecture for MPP databases is that you have a writable store and a read optimized store and a way to convert data. So what this allows you to do is it combines something that is easy to write data into and idempotent in, but optimizes for read. And a very famous paper by Michael Stonepicker out of MIT is the C-store paper that describes this in detail. Later on, we'll share the slides. You could click on the link. Of course, the problem with traditional MPP databases is that most of them are closed source and cost a lot of money once you start to scale out into multiple nodes and with a lot of data. Although I think that some of them are making overtures to have community editions and trying to expand the limits of how much data you could use for free. So that brings us to Cassandra, right? Cassandra, wonderful database. It's horizontally scalable, has very flexible data modeling, like has a lot of support for different types of data type sets. And it's also very easy to operate. And that's something I probably don't need to go into detail, but it's a peer-to-peer architecture, right? That means that every node is the same, which is pretty awesome, right? And so that makes it. That's one of the reasons why it's been so popular for ingesting streaming data and other things, because it can do very high-speed ingestion for all shapes of data, whether it's a narrow kind of data or is very wide kind of data. It can do both, right? And it also has a huge community, has proven storage technology, multi-center replication, a lot of these things. The only thing is that it really supports, the native interface only supports simple queries. Like basically you can get, this is getting better all the time, but you can pull out, it's designed to pull out simple key values, and you can pull out a lot of them, and you can pull out ranges, but it's not designed for massive scans, right? And that brings us to Spark. Spark is a computation framework. Every time I have this slide, I always feel like, increasingly I don't really need to talk about it because all of you guys are now very familiar with Spark, and Martin just gave 30 minutes on what Spark can do, right? The fact that you can do everything in one platform, right, very appealing. So what if we combine both of these technologies, right? You have an excellent storage engine with an excellent the computation engine of today that is super flexible. Right, so what I would say is that Spark really provides the missing, fast and deep analytics piece to Cassandra, right? It allows you to get a lot of insights out of your storage and run all sorts of built-in algorithms. So have a look at how we can actually do this with Spark and Cassandra. The first principle I'll bring out is that compared to, in a traditional database, you think about, you have everything in one box. You have the storage, and you have a query layer, and an SQL query layer, and it's all in one box. What we want to think about is separating the storage and query layers. And this is actually, I think, a pretty powerful concept, because then you can combine a best-of-breed storage solution like Cassandra with the best-of-breed computation platform like Spark, and you can take advantage of both, right? And and you can do interesting things such as, let's say that I want to scale out my querying capability. Traditionally, what you would need to do is you would need to replicate the data storage to multiple clusters and to enable that sort of thing. But especially with memory becoming cheaper, something that you can think about, for example, is let's say that I have multiple Spark clusters that can cache data from Cassandra, then I can scale out my query capability without necessarily doing a very expensive replicating storage and all the things that you need to do. Right. So let's look at this concept in more detail. Spark is Cassandra's cache. And you have data in Cassandra, you want to bring it up into each Spark worker to cache. So Spark SQL is something that appeared with 1.0. It used to be called the Shark project that Ray Nochin worked on. And they decided to rename it and make it an integral part of Spark. And in 1.3, the feature is called data frames. It has an in-memory columnar data store, which is pretty interesting. It stores data in a different format than your native RDDs. It has a huge number of connectors, which is just growing every day, right? It has 2 APIs, which are very interesting. You can still use SQL, but it now has a more of a Scala-ish DSL, which makes it basically it saves you from needing to compile SQL, and it's slightly more type safe, slightly. One thing that Spark SQL has or doesn't have, depending on how you look at it, is that it doesn't have a built-in index into the data, but the way that the indexing works is that there's a data source API that can read from different data sources, and that has the capability it has hooks for doing pruning and filtering. So if it's essentially like the where clause is passed on to the engine. So in the case of Cassandra, for example, if you have a where clause in your SQL, then they get passed down to the data source, and then that can take advantage of any secondary indexes you've defined in Cassandra, which lets you limit the amount of data that you read. And one really cool thing about Spark SQL is that you can write custom UDFs in Scala. This is actually very easy. You define a function, then you call it, register UDF. I don't actually remember the exact syntax, but it's very easy to use. How many people here have used Hive before? So if have you had the experience of working with Hive UDFs or developing them, then like this is like a huge godsend, right? And it integrates very well. And another thing that is extremely powerful is that Spark SQL integrates very well with the rest of Spark. So we can usually take the output of a SQL computation and feed it into, say, MLlib for doing modeling and other things, which it's very easy and integrated. So we'll look at really quickly at connecting Spark to Cassandra is very easy. You can get started with, say, you're using Spark Show. You can use the packages option, and give it a Maven coordinate. And in this case, this is the Spark Cassandra connector, and this will actually go and download all of the dependencies that it needs. So this is super convenient. The only problem with this approach is that it has to pull a lot of dependencies when the shell starts up. The other really important piece is that you want to configure where your Cassandra host is, and that's something that you want to do like when you start. Starting in the latest Cassandra connectors, there is support for data frames. And so this is what it looks like. First, the SQL context, this is kind of code is something that you would have in your own app. But if you're running Spark Shell, you don't need a first line because the SQL context is already created for you. This is the Spark 1.4 syntax. Basically, you do a SQL context.read. And then you basically tell it what kind of data source to read from. By default, it might read from Parquet or something. In this case, we pass it the class name of the input source, which is the spark.sql.cassandra. And the options are what tells the connector where to read from, the key space, table name, and there's some other options. And then you do a load. And At that point, it doesn't load. The load doesn't mean that it's actually loading the data from disk. The load, it's a little bit of a misnomer. It just means that it's going to make sure that the table is there and figure out the schema, that kind of thing. So it should be a very fast operation. And I'll show you guys what this actually looks like later, and there will be a demo at the end. The next line, a register temp table, this is something that you need to do only if you're running SQL, because that gives it a table name. You can actually do, using the Scala DSL, you could do SQL-like things using just the df object. And the cache table will go in a little bit later about why you might want to cache table. And there's an example of running the SQL from that table. One really important thing to note is that Spark doesn't do any caching by default. So if I leave out the cache table line, basically Spark is always going to be reading from Cassandra every single time. So this is how table caching works, and so the what the Cassandra table cache is it's a very high performance. It stores all of your data in a columnar format, right? And the way it works is that, so in Cassandra, let's say you have these logical rows, right? And when the Spark Cassandra connector works, it will read that into memory as an RDD of Cassandra row. Is this okay with everyone so far? Okay. Now, what happens when you do a cache? When you do a cache table, it actually doesn't cache it right away, but it means that in the next read, Spark will then take what you read in as an RDD, which are in the green row boxes, the Cassandra RDD, and it will take that and actually convert it into a columnar format. So instead of being row by row by row, they will now be binary blobs in memory, which are compressed and accessible like one column at a time. And this tends to save a lot of memory compared to the RDD. But the caching, the difference is, so again, normally when you do a read, it will read from disk every time. So it looks like it's populating the entire heap, but that's not what is going on. It's actually an iterator, and it pulls it from disk as it goes along. The caching will save the entire RDD in memory, but in a format that is more read optimized. Yes. Okay, so the question was, is this way of storing or caching data native to Spark SQL, right, as opposed to trying to do it yourself? Yes, so it is native to Spark SQL. It is actually specific to Spark SQL and data frames that if you do cache, it stores it in a special format. And it's different than regular caching of RDDs, which is an important point. And it's possible that it might disappear in the future, but that's not official. Question?
Yeah, I have a question. So, is there a way to configure Cassandra and Spark so that the Spark functions can actually access the local data, not actually with the you know what I mean? So when Spark is actually caching the data from Cassandra,
Well, maybe we'll take that question offline. I think the quick answer, the question was, well, can you get Spark to read from local Cassandra node? I think actually by default, and we'll take this later. If you have Cassandra Spark co-located, the connector is actually smart enough to figure out and try to read local data. It actually reads using token ranges, so it can try to figure out what is local. But we can talk about that later. Oops. So cache tables are really, really fast. I did a test on my laptop, and you'll be seeing this name a lot, GDOUT. How many people have heard of the GDOUT data set? Okay, nobody. Since we're talking about a lot, I'll give it an introduction. GDOUT is a really neat data set. But it's a public open data set that has a lot of, basically a history of all the major political events in the world since the 1970s. And so the caching basically speeds it up by about 1,000x. It's a couple orders of magnitude. And so it's pretty dramatic, but it makes sense if you think about that. When you read it from disk, there's a lot of work that happens. Cassandra has to read it from S table. It has to go through CQL. It has to go through a network, and then has to translate the data into a Spark native format, a Cassandra row. Whereas the caching is in memory and is already in a read optimized format, right? And if you use caching, you can actually get almost interactive speeds on a huge amount of data. I did a study on half of the GDAL data set, which is about 120 million rows. And I don't remember how many gigs of, that's probably 100 or 150 gigs of data on an 8-node cluster. And for really simple queries, you can actually, they actually do like 1 or 2 seconds, which is really, really impressive. One really quick guide to tuning the connector that I'll share. Like this talk is not really about tuning, but the Cassandra.input split size is very important. That basically tells the connector how many rows to pull out for one Spark partition. The reason why this is important is that the number of partitions controls your parallelism in Spark. I mean, you want to have at least one partition per node. Otherwise, you're not getting all the parallelism you are out of Spark. But you don't want too much, because if you have way too many partitions, it won't speed up the job. But what it will do is it will flood Cassandra with requests. And you will find that it will completely starve out any other Cassandra requests. It will make them super slow or timeout, right? Because you're using up all the connections. So the first lesson is take advantage of caching, if you can. But as soon as I say that, I'm going to give you a whole bunch of reasons why you might not want to do caching as well, even though it's really fast. Among the reasons is that caching is not XA, because the data only lives in the heap of the Spark executors. This will probably change in Spark 1.5, by the way, because there's an effort to move some of this off heap. That doesn't really solve the XA problem, but it might. It will get rid of the GC problem. Even though it's really fast after you cache it, it still takes a really long time to read the data from Cassandra. You also need extra memory to do the conversion from a Cassandra row into the cache format. The other thing is that because the cache format is special, it is a special kind of RDD, it doesn't really work well with new data. So let's say that I have cached everything from the last 30 days, but now I want to add some data into Spark. And there's something called a union in Spark. You can load new data and union a new RDD with an old RDD. But this doesn't really work well with cache tables. You can kind of make it work, but then it slows down. So it's not really a use case that they've really thought of, right? So can we do? So the question is really, can we do better? And as a side note, if you don't have enough memory to fit a cache table, Spark is smart enough to save it to disk. And this seems kind of redundant because now we're reading from disk again, but it turns out that this is actually still much faster than reading directly from Cassandra. But even though it's saved to disk, partly saved to disk, it doesn't make it any more XJ, because the metadata for this the cache table, it still lives with one Spark context. So it only lives for the lifetime of that context. Does anyone know what I'm talking about when I say Spark context? Yes, mostly? Okay, yeah, just one Spark application. As I said before, doing an RDD.cache is not the same as caching a table using Spark SQL because that saves it in a special format. The RDD.cache, what it does is it takes each object in an RDD, which is a Cassandra row object in this case, and it serializes using whatever serialization you define, like such as Java serialization or Creo or something. So it's a different format than the columnar one, and it takes up more takes up more space. A quick note about secondary indexing. Secondary indexing, does this work with caching? So depends on what you mean. I would say for running ad hoc queries, not really, because what the caching does is that it caches the RDD that you load from disk. If you pass to Cassandra a where clause in your first query, and that where clause restricts to, say, 10% of your data, then 10% of your data will end up being cached in memory, which might not be what you want. Quick question. I'm sorry, could you say that?
Secondary indexes in Cassandra, I thought that they were performance reducing and that they required searching the entire array for data. So that's different.
Okay, the question is, I thought that secondary indexes were performance reducing. Interesting.
Because if I use secondary indexes and I'm not using the partition key to fetch the data from Cassandra, so I'm not going to just one node, I can go into
I'll just give a really quick answer, and then we can talk about it later, or I might refer you to my friend who's some data stacks. But yes, I think you're right that the secondary index mechanism requires a lookup of every node. So I think it really depends on the ratio of the data that you want filtered versus how many nodes you have. Do you know what I mean? Like, it's like the cost of going to every node might still be very low compared to reading out just a very small chunk of data versus having to scan an entire table. A really quick mention about Tachyon. How many people have heard of Tachyon? Awesome. Maybe like a third, right? So Tachyon, if you look at this diagram, it's like a layer that sits between Spark and another data source. And what Tachyon is an in-memory cache. It's really originally designed for HDFS, and it works best for files. But it keeps data off heap, and then it has a kind of daemon so that multiple JVM processes can share that data, which is really, really neat. So this Tachyon solves the HA problem. Instead of keeping data in one Spark, tied to one Spark context and in the heap or off heap, it keeps the data, off heap, but makes it such that other processes can share it. So this is great. But can we take advantage of this right now? The short answer is not really. What do you cache in Tachyon? Like if I go back to this diagram, the diagram is not quite right because if I read data out of Cassandra using regular CQL, it will come back. It's really designed for applications, right? CQL. So it will come back as, I don't know, let's say your case class of person with first name, last name, whatever. Now, if I want to cache it in Tachyon, I would have to serialize it again into some binary format, right? Or maybe there's some way to insert it between. I think the way to really use Tachyon is you would want to read the raw data from Cassandra and use Tachyon as a row cache. Cassandra has its own row cache, but if that's something that's not designed for Spark, right? So if you had Tachyon in front of Cassandra reading the raw data, then you can actually share that amongst multiple Spark nodes. But this is something that would require a large amount of work. So I love this quote from Linus, that good programmers worry about data structures. So what I would challenge everyone to think about today is, are we thinking holistically about data modeling and caching, and like how do we make the whole system work? Because sometimes it feels like every component designs its system by itself, right? And like we're trying to fit a lot of things together that don't necessarily fit together, and no one's thought about like the whole picture, right? So how can we do better? than either of these two architectures. So efficient columnar storage. And first, I'll quickly clear up what I mean by columnar. So how does Cassandra store your SQL tables? Let's say that you had this SQL table which has a first name, last name, age, an employee ID, a department. And maybe we want to key by department and employee ID. And the two-part primary key, I think everyone probably knows this if you know Cassandra, but the two-part means that the first part of the primary key is the partition key that determines on what node your record goes. And the second part of the key is called a clustering key that basically tells Cassandra to sort the records by employee ID order. So the way that Cassandra 2.x actually stores your data is this. If I go back really quick, you see that the employee ID is the clustering key. So if I look at, this is the physical layout of a Cassandra table, not the logical layout. And you'll see that the partition key is the department, so that's like sales or engineering. And then all the other records are laid out in a physical row. But this is the interesting part, is that what Cassandra will actually do is that, so every cell has a column name as well. And it will actually prepend your clustering key, which in this case is the employee ID. So let's say that logical record 1 is employee ID 01, is Bob Jones. And what Cassandra would do is that it will store Bob in one column, it will store Jones in another column, and the way that it disambiguates between those two is that it will append the column name, in this case first or last, and an age. So this is the actual physical layout. What this allows Cassandra to do is that if I was to insert only the last name, for example, let's say that I wanted to update Jones to, I don't know, Joneses or something, right? Then that allows Cassandra to address only Jones and update only that column. And the other thing you'll notice is that all of the items in record 2 comes after record 1, but that each row is stored contiguously, meaning that all the fields appear in one cell after another, and then you get the next row, and you get one cell after another. Let's say that you wanted to run an analytical query and you wanted to analyze the age field only. Let's say you want to get the average age or distribution of ages. What Cassandra has to do is that it still has to read. You can say, I'm going to read only the age cells. But because of the way that it's laid on the disk, essentially Cassandra still has to read the entire physical row in order to return a subset of data to you. So basically, Cassandra is really a role-based, OLTP-oriented data store. If you, unless you know how to take advantage of it. And Michael Stonebraker said the traditional role-based data storage approach is dead. I'll just go over this really quickly. But what the columnar storage way of doing things is that I would store items from a column together. So for example, let's say you have a name and age. Again, I would put the ages from subsequent records together in one place and a name in another place. What it might look like in Cassandra is that, this is one example, right, is that the row key might actually be the column name. And so there's name. And then I would store, and that way if I want to pull out all the ages together, I would just pull out the ages, and it would only need to do IO for age. And one thing that columnar format brings you, if you're familiar with Parquet, is that it gives you huge savings in terms of space. You might know that one of the reasons people like Parquet is that it actually is compresses data down much smaller than a lot of, like, let's say we just dumped a text file. And one of the reasons why it's able to do that is because it's able to look at a set of, let's say all the ages together, and it can figure out, I only need to store like this in so many bits, right? Because all the numbers are within this range. So it can do a lot of smart kinds of compression by looking at data as a whole. So why isn't, if columnar storage is so promising, why isn't everyone doing this? I think the main reason is that most of our infrastructure is still row-based. Spark, for example, is row-based, and the columnar format is, there isn't anything that really works with NoSQL stores. So I'll share with you. You guys can. I'll skip over. We're starting to run out of time, so I'm going to skip over the some of the stuff so you can find the links later. But I did a study of the GDAL data set, right? And with several different layouts, and with several different layouts, with one layout with CQL, another layout with CQL, narrow and wide, versus a columnar layout. And what we found was that using a columnar layout dramatically decreases both the ingest and the read speeds. And it also uses up less space, about like 5 to 10x less space. Let me skip over some stuff really quickly. So to share with you the project I'm working on now, this project is called FiloDB. And what you can think of it as is it's a modern columnar data store built on Cassandra and Spark. And it is columnar in the Parquet sense that it uses a storage layout where it can minimize I/O for OLAP queries. Right. It is, I'm proud to say that it's 100% reactive, that it uses the type-safe stack. It uses Akka, Scala, futures, the Phantom Cassandra library, which is a future-based Cassandra library. And it uses Spark SQL as your query engine, so it's very easy to use, as well as data frames for input and output. How it compares to Parquet, for example, is that it will give you comparable read performance. Like if I look at it on, say, a local host, you see that what you see is in a sec that performs about the same, but it has a lower memory requirement because it's based on smaller block sizes, which also makes it more suitable for more like IoT applications where you have wider types of data. And as of right now, it supports like much fewer types, but that's something that we hope to grow out. And where it fits in is that you would still want to use Cassandra for key value lookups, that pre-aggregation, that kind of things. But then you can use that existing infrastructure with Cassandra and Spark for doing ad hoc and more complex types of analytical queries. And this would allow you to simplify your architecture from, let's say it's a typical Lambda architecture where I'm writing into 2 pipelines, where the incremental views might be going to something like Cassandra, and the pre-computed views has an entire Hadoop stack as well. It allows you to simplify your architecture to something like this, where I am using Spark streaming and writing to Cassandra, and I can use it for both. I mean, if you compare this picture to this picture, you can like just count the number of boxes, right, and see how many fewer boxes you have to deal with, right? That you're looking at using Cassandra for both OLTP as well as OLAP. And you can do exactly one's ingestion from Kafka because of the idempotency that you can write values again and again, and it won't, and it will replace the existing content. So I'm going to go really quickly into a into a demo that shows you basically. Let's see. I think you guys can see this. All right. So basically, I have on the top box, I have a FiloDB connected to Cassandra with a data frame. And this is 4 million records of the GDAL data set hosted locally, all 60 columns. And I'm going to do a really simple query, which is just to count all the items in month year, right? And this will run in about half a second, right? And if I do the same thing with Parquet, which is df2, which is off of a local Parquet file, it does a whole bunch of stuff. It takes about 1 second, kind of like in the same ballpark, right? And in the bottom window, I have a Spark Cassandra connector, which is loaded using something. Okay, I won't pull this up because, but you can find me if you're interested. But basically, this will pull up. This reads from regular Cassandra SQL table, and we're going to do the exact same query. And you'll find that this will take a couple of minutes to run. Yep, and that's it. Thank you very much. I don't know if we have time for questions or we'll just take it offline. Okay, so we'll take questions offline. Thanks.